Welcome back, class. To start off today, I want to talk about this graph of this function, taken from a meteorology textbook. And what this function does is to describe what the average temperature is as a function of the altitude, that is, how far above the ground you are. Now note the units here. The units of the input are in kilometers, and the units of the output are in degrees Celsius. So when you look at the input and you see that the far right input is 100, that's talking about the average temperature 100 kilometers above the surface of the Earth. Just for comparison, no commercial airplane has ever gone more than 20 kilometers above the surface of the Earth, and most of them actually go a great deal lower than that. So the heights in this graph, once you get even a little bit to the right, are very, very high. So before we get into talking about the derivatives of this function and what those mean, I want to talk about the values of this function at a few select points and how we can think about them. So what's t of 0 mean? T of 0, so the input here is in kilometers, and the output is in degrees. And if you look at the graph, this is about 15, and so it's about 15 degrees Celsius. Okay. And so what is an altitude of 0? An altitude of 0 would be on the surface of the Earth. And so this is saying that the average temperature on the surface of the Earth is about 15 degrees Celsius. Okay. Just to put that in Fahrenheit, which you might be more familiar with, this is about 60 degrees Fahrenheit. So across the whole Earth, across the whole year, the average temperature is about 60 degrees Fahrenheit. So what's T of 4? So here we're talking about an altitude of 4 kilometers. For reference, if you're a recreational skydiver, you would skydive from a height of about 4 kilometers. And so this number here, this T of 4, this is going to be giving you the average temperature of the air from where you jump out of the plane. And that, if you read off the chart, is about minus 9 degrees Celsius, which translates to about 15 degrees Fahrenheit. Now, just from 0 to 4, you can observe what's happened, which is namely, we've gone up in altitude, and the temperature has gone down. Okay, namely, it's gotten colder. In fact, as you jump out of the plane, it is quite cold. That is what this is telling us. But then, as you fall down from the plane, it gets warmer. Now, I mentioned before that no commercial airliner has ever gone more than 20 kilometers in the air. In fact, the highest a commercial airliner has ever regularly flown is about 18 kilometers in the air. Okay, and at 18 kilometers in the air temperature is minus 55 degrees Celsius, which is about negative 67 degrees Fahrenheit. So definitely note, when you go skydiving, you should not be jumping out of an airplane that is in the air at the usual passenger plane height. You should be jumping out of an airplane that is much, much lower to the ground. So this is the values of the function. I now want to talk about the derivative of the function. So I'm just going to pick 4 to focus on for now. And so t prime of 4 works out to be about negative 6. And what are the units? Well, it's the units of the output over the units of the input. So it is in degrees Celsius per kilometer. Now, there are really 2 pieces to this derivative, and I want to talk about them separately. So one piece is the negative, and the other piece is the 6 degrees Celsius per kilometer. The negative is going to tell me about the direction of the change, and this 6 degrees Celsius per kilometer, this is going to tell me the how fast piece. So let's start by deciphering the negative. And so this is something we talked about all the way when we talked about slopes, is what does it mean for a slope to be positive, and what does it mean for a slope to be negative? And I think the best way to think about it is positive slope means the input and output move in the same direction. The negative slope, or a negative derivative, means that the input and output move in opposite directions. So in this case, we see that t prime of 4 is negative, and so that is telling us that the input and output move in opposite directions. So that is when you jump out of the plane, when you're at 4 kilometers, the altitude and the average temperature move in opposite directions. Now, when you jump out of the plane, your altitude goes down, and so that means the temperature goes up. Okay. So as you fall, the temperature goes up. On the other hand, if instead of jumping out of the plane with a parachute, you jumped out of the plane with a jetpack and went up, then your altitude would increase, and since these two move in opposite directions, the temperature would decrease. That is what this negative means here. What does the 6 mean? So the 6 degrees Celsius per kilometer is telling us that at the current rate, every kilometer change in altitude gives a 6 degrees Celsius change in temperature. Note this wiggly phrase, at the current rate. This is the equivalent of what we talked about way back at the beginning when we talked about speedometers. Namely, remember when we talked about the speedometer in a car, and we said when the speedometer in the car reads 60 miles per hour, that 60 might have no real-world meaning, because what it's really saying is that if you continued at exactly the same speed for an hour, you would go 60 miles. But you might not continue at exactly the same speed. In the same way, this 6 degrees Celsius per kilometer that shows up in the derivative is telling us that if the rate continued exactly as it is now, then every kilometer you went up would change the temperature by 6 degrees Celsius, and every kilometer that you went down would change the temperature by 6 degrees Celsius. Now, you really need both of these pieces together, the sign and the number, to really get your complete picture. Okay. Because this is now saying, if you want, every kilometer you fall, the temperature will go up by 6 degrees, or every kilometer you go up in your jetpack, the temperature will fall by 6 degrees. And that is, again, if the exact rate of change that is happening when you're at 4 kilometers stays the same. And so, again, when you look at this of 4 is telling you where you start. And so this is telling me how things change at an altitude of 4 kilometers. At some other altitude, the change will likely be different, as we'll see. Now let's jump up and let's talk about what happens at 18 kilometers in the air. 18 kilometers in the air, we're now talking about the highest altitude that commercial airliners have regularly flown. Here, actually, if you look at the graph, you can probably tell me what this derivative is going to be. Namely, this derivative is going to be 0. A derivative, remember, is a measure of change. How is the value of the function going to change with changes in the input? A 0 is the statement that there is no change. And so what this is saying is that at an altitude of 18 kilometers, changing your altitude won't change the temperature at all. Now, of course, if you change your altitude a lot, that won't still be true. For example, if you change your altitude all the way down to 4, we know that it will be quite a bit warmer. But really what this is saying is small changes in the altitude will give no change in the temperature. And if you look at this flat part of the graph here near 18, then you'll see that this is true. I can go up a little or down a little, and because the graph here is just perfectly horizontal, that means the temperature is staying exactly the same. All right, so we've talked about T prime of 18. Let's now talk about T prime of 40 kilometers. So what's 40 kilometers? 40 kilometers is the highest anyone has ever skydived from. Again, this is 10 times as high as the typical skydiving thing, but as some sort of sponsorship for some sort of energy drink, someone jumped out of a plane, or not a plane. Someone jumped out of some sort of vessel from 40 kilometers. And as it would happen, T prime of 40 is 2.5 degrees Celsius per kilometer. And it can be easy to miss, but remember there are two pieces of information here. There's the rate, but there's also the sign, which in this case is a plus sign. And I want to first talk about this plus sign, because this plus sign is really weird and counterintuitive to me. What does this plus sign mean? The plus sign here means that at a height of 40 kilometers, the change in altitude and the change in temperature go in the same direction. So in particular, when this stunt jumper jumps out of their vessel at 40 kilometers in the air and they start falling, that means their altitude starts going down. And since the derivative here is positive, that means the temperature also goes down. And so as this person jumps from 40 kilometers and they start falling, their perception of the temperature goes down. Now, I want to remind you, this is the opposite of what happened when we talked about someone jumping out of a plane at 4 kilometers in the air. There, the derivative was negative, and so as the person fell from a height of 4 kilometers, the temperature actually went up, because there, the altitude and temperature moved in opposite directions because of this minus sign. Now, all of these words I'm saying are things you can see if you look at the graph. So if you look at someone starting at an altitude of 40 kilometers, they'll have the temperature about here, which will say that the temperature will be about minus 25 degrees Celsius, which is cold, but not as cold as it's going to be. Because then as they fall, their altitude goes down, and as they fall from an altitude of 40 kilometers to an altitude of 20 kilometers, the temperature around them drops from about minus 25 degrees to about minus 55 degrees. And then, as they continue falling back towards the Earth, now it goes the other direction, and it starts getting warmer, until they mercifully land on the surface and hopefully it is warm for them. This is what derivatives do. They describe for us at a particular time how the change works, both its magnitude and its direction. In the next video, I'm going to do a couple of examples from economics to show you how people in business think about derivatives and think about these kinds of changes. But that's all for now. I'll see you next time.